1 billion years ago, Earth had eukaryotic cells, complex cells with nuclei and mitochondria, cells with the energetic capacity to support complexity, cells that theoretically could grow large, could cooperate, could become multicellular. The genetic toolkit was ready. The cellular machinery was ready. Everything necessary for complex life was in place. And for 800 million years, nothing happened. Evolution simply idled. Single cells divided, reproduced, drifted in the oceans, going through the motions, but never taking the next step, never becoming complex, never building bodies, never growing large enough to see with the naked eye. 800 million years. That's longer than the entire time from the Cambrian explosion to now, longer than the age of dinosaurs and mammals combined. An incomprehensible span of time where life, despite having every tool it needed, just waited. Stagnant, static, boring. Geologists call this the boring billion. And it's one of the greatest mysteries in evolutionary history. Because evolution doesn't stop, except it did. For 800 million years, the fossil record shows almost no change. Stromatolites that look identical across hundreds of millions of years. Bacteria that don't evolve. Algae that don't diversify. What could freeze evolution so completely? What environmental prison could lock life into stasis for so long? And what catastrophe finally broke the freeze and unleashed the most explosive period of evolutionary innovation in Earth's history? This is the story of how Earth became boring and how it escaped. Before we dive in, if you've been following this series on Deep Time, please consider subscribing. Your support helps us continue exploring these forgotten chapters of our planet's history. Thank you. 1 billion years ago, Earth looked nothing like it does today. But more unsettling than how different it looked is how little it was changing. Let's start with the obvious: the continents. Today, we have 7 major landmasses scattered across the globe: North America, South America, Africa, Eurasia, Australia, Antarctica. They're separated by vast oceans: the Atlantic, the Pacific, the Indian. This distribution creates a planet with enormous coastal perimeters where land meets sea. And those coastlines matter, because coastlines are where weathering happens, where rivers deliver nutrients to the oceans, where biological productivity concentrates. Coastlines are, in a very real sense, where the action is. 1 billion years ago, there were no coastlines, not in the way we think of them. Because 1 billion years ago, nearly all of Earth's continental crust was jammed together into a single, massive supercontinent. We call it Rodinia, from the Russian word for homeland, and it was huge, larger than any supercontinent since, stretching from pole to pole, roughly 13,000 kilometers north to south. Imagine a landmass the size of Asia, Africa, and the Americas combined, all fused together, all locked in place. And here's the problem. When you have all your continents in one place, you don't have coastlines. You have a coast, singular, a thin ribbon of shoreline wrapping around the perimeter of one massive landmass. And the interior of Rodinia, thousands of kilometers from the nearest ocean, was a desert. Not metaphorically, literally, a hot, dry, lifeless wasteland. No rain reached the interior. No rivers drained it. No weathering occurred. It was geologically dead. The evidence for Rodinia's existence comes from paleomagnetic data and matching geological provinces. When geologists analyze the magnetic minerals in billion-year-old rocks from different continents, they find something remarkable. The magnetic orientations match. Rocks from eastern North America align with rocks from Western Australia. Rocks from Siberia match rocks from Western North America. It's like a jigsaw puzzle. The pieces fit. And when you put them together, you get Rodinia. John Rogers, a geologist at the University of North Carolina, was one of the first to propose the existence of a Neoproterozoic supercontinent in the 1990s. He called it Rodinia and spent years working out the configuration. Which continents went where, how they fit together, and what he found was unsettling. Rodinia wasn't just big, it was stable, locked together by ancient mountain belts, collision zones where continents had smashed together and welded shut. For hundreds of millions of years, Rodinia just sat there, not moving, not breaking apart, not doing much of anything. And that stability was a death sentence for the biosphere. Because life doesn't thrive on stability. Life thrives on disturbance, on turnover, on the churning dynamic chaos of tectonic activity. Rodinia shut that down. Consider the ocean circulation. Today, ocean currents flow between continents, driven by temperature differences and the Coriolis effect. Warm water moves from the equator toward the poles. Cold water sinks and flows back along the bottom. This circulation distributes heat and nutrients globally. It oxygenates the deep ocean. It drives weather patterns. It's the engine of Earth's climate. But 1 billion years ago, with Rodinia blocking most of the equatorial and mid-latitude zones, ocean circulation stalled. The deep ocean became stratified. Warm, oxygenated surface water sat on top. Cold, stagnant, anoxic water filled the depths. And between them, a boundary layer, a chemocline. Below that line, there was no oxygen, no life, just sulfides and methane and darkness. We know this from geochemical proxies, iron speciation data, sulfur isotopes, biomarkers, all pointing to the same conclusion. The deep ocean during the boring billion was dead, anoxic, a vast three-dimensional desert. And the only places where life could survive were the shallow coastal shelves and the surface waters of the open ocean. A thin film. A biological veneer clinging to a mostly lifeless planet. But even that veneer was struggling because of phosphorus. Phosphorus is one of the essential elements for life. It's in DNA, in RNA, in ATP, the molecule that stores and transfers energy in every living cell, in cell membranes. You can't build life without phosphorus. And the only source of phosphorus for the oceans is weathering, specifically the weathering of continental rocks. Rain falls on mountains. The water, slightly acidic, dissolves minerals, including apatite, a phosphate mineral. That dissolved phosphorus gets carried by rivers into the oceans, where it fertilizes phytoplankton and algae, which form the base of the marine food web. But here's the catch. Weathering requires mountains, because mountains create topographic relief, steep slopes, fast-flowing rivers, rapid erosion. When you have active tectonic activity, when continents are colliding and rifting and building mountain ranges, you get weathering. You get phosphorus delivery. The biosphere gets fed. Rodinia had no mountains, or rather, it had old mountains, worn down, eroded flat. The great mountain building episodes that had assembled the supercontinent happened between 1.3 and 1.0 billion years ago. By 1 billion years ago, those mountains were gone, reduced to low rolling hills, and with no active collision zones, no new mountains were forming. The supply of phosphorus to the oceans slowed to a trickle. Noah Planavsky, a geochemist at Yale, has spent years studying phosphorus availability through Earth's history. In 2014, he published a paper showing that phosphorus concentrations in the oceans during the boring billion were among the lowest in the entire Proterozoic. Low phosphorus means low biological productivity, which means less oxygen production by photosynthesis, which means lower atmospheric oxygen levels, and the oxygen data confirms this. Between 1.8 billion and 800 million years ago, atmospheric oxygen levels were stuck around 10 to 15%. Not the 21% we have today, not even close. Just enough to support aerobic life, but not enough to allow it to grow large or complex. The biosphere was on a starvation diet, metabolically limited, going nowhere. But here's the truly strange part. It's not like life had disappeared. Bacteria were everywhere. Cyanobacteria carpeted the shallow seas. Algae floated in the surface waters. And crucially, eukaryotes existed. Remember eukaryotes? Those complex cells with nuclei and mitochondria that we talked about in the 2 billion years ago video. They'd been around for at least 1 billion years by this point, maybe longer. Genetic and fossil evidence places the origin of eukaryotes somewhere between 2.1 and 1.6 billion years ago. So for hundreds of millions of years, Earth had eukaryotic life. Cells with the energetic capacity to support complexity. Cells that, theoretically, could grow large, could cooperate, could become multicellular. And yet, for almost 1 billion years, they didn't. They stayed single-celled, drifting, dividing, going through the motions, but never taking the next step, never becoming complex. Why? What was holding them back? The answer, it turns out, has to do with sex, or rather, the lack of it. Today, most eukaryotes reproduce sexually at least part of the time. Sexual reproduction involves meiosis, a special type of cell division that shuffles genes, creating offspring that are genetically different from their parents. This genetic recombination is evolution's greatest innovation. It creates variation. And variation is the raw material on which natural selection acts. Without sex, without genetic recombination, evolution slows to a crawl. You're stuck with whatever mutations randomly occur. And most mutations are neutral or harmful. Beneficial mutations are rare. For most of the boring billion, eukaryotes reproduced asexually. They divide, splitting into 2 identical daughter cells, clone after clone after clone. No genetic mixing, no innovation, just endless copies. It's efficient, it works, but it's an evolutionary dead end. Because when the environment changes, when conditions shift, asexual organisms can't adapt fast. They don't have the genetic diversity to respond. They stagnate. And that's exactly what happened. For 800 million years, eukaryotic life stagnated, stuck in an evolutionary holding pattern, waiting for something to change, waiting for a catalyst. And then, around 1.2 billion years ago, something did change. Something small, something invisible to the naked eye, but something that would eventually transform the planet. Life invented murder. That sounds dramatic, but it's accurate. For billions of years, life on Earth had been cooperative, or at least non-violent. Bacteria and algae didn't eat each other. They competed for resources, sure, light, nutrients, space, but they didn't actively hunt and kill. They didn't predate. The biosphere was, in a sense, peaceful. A vast floating garden of photosynthesizers and decomposers, all coexisting in a slow metabolic dance. But around 1.2 billion years ago, some eukaryotic cells developed a new trick. They started engulfing other cells, not for symbiosis like the original endosymbiotic event that created mitochondria, but for food. They'd wrap their cell membrane around a smaller cell, pull it inside and digest it, absorb its nutrients, kill it. This was phagocytosis, the ability to eat, and it was revolutionary. The evidence comes from a fossil called Bangiomorpha, found in rocks from Arctic Canada, dated to 1.2 billion years ago. Bangiomorpha is a red alga. And it's not just any alga, it's multicellular, a chain of cells connected end to end, forming a filament. And crucially, it shows signs of differentiation. Some cells in the filament are different from others, specialized. Some are photosynthetic, others are reproductive, and some, possibly, are defensive. Why would you need defensive cells? Because someone is trying to eat you. Predation. Nick Butterfield, a paleontologist at Cambridge, has argued that Bangiomorpha represents the earliest evidence of complex multicellularity driven by predation pressure. If something is trying to eat you, being bigger helps. Being harder to swallow helps. Developing structures that deter predators helps. And the easiest way to get bigger fast is to stick together. Multicellularity, not as a cooperative venture, but as an arms race, an evolutionary Red Queen scenario, where you have to keep running just to stay in place. And once predation starts, it doesn't stop. It escalates. Prey evolve defenses, predators evolve counters, defenses get more elaborate, predation gets more sophisticated. And suddenly, evolution, which had been idling for hundreds of millions of years, kicks into gear. The boring billion wasn't boring anymore. It was a war zone, small, microscopic, but a war nonetheless. And then, around 1 billion years ago, something even more important happened. Eukaryotes figured out sex. We don't know exactly when sexual reproduction evolved. The fossil evidence is sparse. You can't easily fossilize the act of genetic recombination. But there are clues. Bangiomorpha, that 1.2 billion-year-old red alga, shows structures that look suspiciously like sexual reproductive cells, spores. And spores in modern red algae are produced through meiosis, the genetic shuffling that defines sex. If Bangiomorpha was sexual, and most paleontologists think it was, then sex, true sexual reproduction, is at least 1.2 billion years old, maybe older. And once sex appeared, evolution had a new engine. Genetic recombination meant variation. Variation meant adaptation. Adaptation meant survival in changing conditions. Sexual organisms could evolve faster, respond to environmental pressures, innovate. But here's the paradox. If sex appeared 1.2 billion years ago, why didn't complex life explode immediately? Why did it take another 600 million years for animals to appear? Why did the boring billion drag on for so long after the invention of the two most important evolutionary innovations, predation and sex? The answer, frustratingly, is that we don't entirely know. But the best guess is that the environment was still limiting. Yes, eukaryotes now had the tools to evolve complexity, but they were still trapped in a low-nutrient, low-oxygen world. Rodinia was still blocking ocean circulation. Phosphorus was still scarce. Oxygen was still too low to support large, energetically expensive multicellular organisms. The genetic potential was there, but the environmental conditions weren't. Life was like a runner crouched at the starting line, muscles tensed, ready to explode forward. But the gun hadn't fired yet. The planet hadn't given the signal. And so, life waited. For hundreds of millions of years, it waited. And then, around 900 million years ago, something shifted. Oxygen levels started to rise. Not dramatically, not to modern levels, but noticeably. From around 10% to maybe 15, maybe 18%. Geochemists call this the Tonian oxygenation event. Tonian, from the Greek for stretch, because this was the period when Earth was stretching, getting ready to break apart. The cause of the oxygen increase is debated. Some researchers think it was volcanic, that a surge in volcanic outgassing released carbon dioxide, which stimulated photosynthesis. Others think it was biological, that the evolution of more efficient photosynthetic algae may be driven by predation pressure, increased oxygen production. Still others think it was tectonic. That the early stages of Rodinia's breakup created new coastlines, increased weathering, delivered more nutrients to the oceans, which boosted productivity. Whatever the cause, the effect was clear. More oxygen meant more energy available for complex life. It meant a thicker ozone layer, better UV protection, safer conditions for organisms living in shallow water. It meant the possibility, for the first time in hundreds of millions of years, of growing large. And it meant that the stalemate was ending. Rodinia, that vast, stable, stagnant supercontinent, was beginning to crack. The breakup of a supercontinent is one of the most dramatic events in geology. And it doesn't happen quickly. It's not like dropping a plate. It's more like slow-motion tearing, driven by heat from below. When a supercontinent sits in one place for hundreds of millions of years, it acts like an insulating blanket. Heat from the mantle, generated by radioactive decay, gets trapped beneath the continental crust. It builds up, and eventually it has to escape. Around 900 million years ago, the mantle beneath Rodinia began to bulge upward. Plumes of hot rock, rising from deep in the earth, pushed against the underside of the continent. The crust stretched, thinned, cracked. Rift valleys formed. Magma oozed up through the cracks, creating volcanic chains. And slowly, inexorably, Rodinia began to split apart. The evidence for this is written in the rocks. In eastern North America, in the Appalachian Mountains, there are ancient rift basalts dated to around 750 million years ago. In Australia, similar rocks. In Siberia, the same. All pointing to a coordinated breakup event. Rodinia wasn't just fracturing in one place, it was fragmenting everywhere, like a windshield after a rock hits it, cracks spreading outward in all directions. And as the continents pulled apart, something remarkable happened. New coastlines formed, lots of them. Where there had been one continuous landmass, now there were dozens of fragments, each with its own perimeter. And more coastline meant more weathering, more rivers, more nutrient delivery to the oceans. Phosphorus, which had been scarce for hundreds of millions of years, suddenly became abundant. Noah Planavsky's data shows a sharp increase in ocean phosphorus concentrations starting around 800 million years ago. The nutrient tap had been turned back on. The oceans were being fertilized, and the biosphere, starved for so long, responded. Algal blooms spread across the shallow seas. Photosynthesis ramped up. Oxygen production increased, and with more oxygen came more opportunity. Larger organisms, more complex structures. Ecological niches that had been empty for eons suddenly became fillable. But the breakup of Rodinia didn't just deliver nutrients and oxygen. It also delivered something else, something far more dangerous. It triggered the worst climate catastrophe in Earth's history. Because when continents rift and separate, they change the planet's albedo, its reflectivity. When you have one giant landmass at low latitudes, it absorbs a lot of sunlight. Dark land, warm planet. But when that landmass breaks apart and the fragments drift toward higher latitudes, toward the poles, you get ice. And ice is white, reflective. It bounces sunlight back into space. And the more ice you have, the more sunlight you reflect, the colder the planet gets, which creates more ice, which reflects more sunlight. A runaway feedback loop, the ice albedo feedback. And around 717 million years ago, that feedback loop went critical. Earth froze, completely. From pole to equator, ice sheets kilometers thick covered the oceans. Glaciers ground across every continent. It was Snowball Earth, again. But this time, it was worse than the Huronian glaciation we talked about in the 2 billion years ago video. This time, the freeze lasted longer, was colder, and came closer to ending all complex life on the planet. Geologists call this event the Sturtian glaciation, named after rock formations in Australia where the evidence was first found. Diamictites, glacial deposits, drop stones, boulders carried by icebergs and dropped into ocean sediments. And the kicker, these deposits are found at paleo-equatorial latitudes. Rocks that, according to paleomagnetic data, were sitting near the equator 700 million years ago. And they're full of glacial signatures, ice. At the equator, the only way that happens is if the entire planet is frozen. Paul Hoffman, the same geologist who worked on the Huronian snowball, spent years studying the Sturtian and its younger sibling, the Marinoan glaciation. And his conclusion was stark. These weren't just bad ice ages. They were near-extinction events, global, total. The kind of thing that should have ended complex life before it even got started. Average global temperatures during the Sturtian are estimated at -40 to -50 degrees Celsius. Colder than the Huronian. The ice was thicker. The freeze lasted longer. 50 million years. Maybe 100 million. The exact duration is debated. But what's not debated is the severity. This was as close as Earth has ever come to being a dead, frozen ball spinning silently through space. But life survived. Somehow. Again. Just like it did during the Huronian. Except this time, we have a better idea of how. The obvious refugees were the same as before, hydrothermal vents. Deep beneath the ice, where the ocean floor was volcanically active, vents continued to pump heat and chemicals into the freezing water. And around those vents, microbial life clung on. Thermophiles, chemosynthesizers, the usual suspects. They'd survived the Huronian. They survived the Sturtian. They'd probably survive anything. But there's evidence for another refuge. A stranger one. A place that shouldn't have been habitable, but was. Inside the ice itself. In modern glaciers, particularly in Antarctica and Greenland, scientists have found something remarkable. Small pockets of liquid water trapped within the ice. They're called cryoconite holes, and they form when dark particles, dust or volcanic ash, or even microbial cells, land on the ice surface. These dark particles absorb sunlight, they heat up, and they melt a small pocket of ice around themselves, a tiny pool, a few centimeters across, sometimes larger. And in those pools, life thrives. Algae, bacteria, even tiny multicellular organisms, all living inside the glacier, using the heat from absorbed sunlight to maintain a liquid refuge in an otherwise frozen world. It's surreal, beautiful, alien, and it's happening right now in places like the Antarctic dry valleys. And there's evidence it happened during the Sturtian. Organic biomarkers in Sturtian age glacial deposits include compounds produced by photosynthetic algae. Algae that presumably were living in cryoconite holes within the snowball ice sheets, photosynthesizing, reproducing, waiting for the world to thaw. This is a new survival strategy, one we didn't see during the Huronian. And it suggests that by 700 million years ago, life had diversified enough, had developed enough resilience that it could survive even inside a global ice sheet. Not thriving, not expanding, but surviving, holding on, patient. But patience has limits, and after 50 to 100 million years, the planet finally broke the freeze, just like it did after the Huronian. Volcanic outgassing, continuing through the entire glaciation, slowly built up carbon dioxide in the atmosphere. And eventually, the greenhouse threshold was crossed. The ice started to melt, and once it started, it accelerated. Runaway deglaciation, ice collapsing, sea levels rising hundreds of meters, the entire planet transitioning from frozen to tropical in maybe a few centuries, maybe less. And then, just as the biosphere was recovering, just as oxygen levels were rising and nutrients were flooding the oceans and complex life was starting to diversify, it happened again. Earth froze. A second time. The Marinoan glaciation, 635 million years ago. Another snowball. Not quite as long as the Sturtian, maybe 15 to 20 million years, but just as severe, just as total. Back-to-back global glaciations, separated by perhaps 50 million years of recovery. 2 punches. And life, barely getting back to its feet after the first, got hit with the second. Why did it happen twice? That's one of the great mysteries. Some researchers think it's related to Rodinia's breakup, that the configuration of continents during the breakup created a climate system that was inherently unstable, that Earth kept oscillating between greenhouse and icehouse states, unable to find equilibrium. Others think it's related to carbon cycling, that the deglaciation after the Sturtian was so intense, so rapid, that it drew down atmospheric carbon dioxide too quickly, triggering another freeze. Whatever the cause, the effect was brutal. Life got hammered. Twice. And when the Marinoan finally ended, when the ice melted for the second time, the planet that emerged was transformed. Not just geologically, not just climatically, but biologically, because the deglaciation events, both of them, were apocalyptic. When you melt a global ice sheet that's been accumulating volcanic carbon dioxide for tens of millions of years, you don't get a gentle thaw. You get a super hot greenhouse, temperatures spiking, oceans warming. And because the oceans had been stagnant and anoxic for so long, full of dissolved carbon dioxide, the sudden warming triggered massive outgassing. Carbon dioxide bubbling out of the ocean like a shaken soda bottle. The atmosphere, already loaded with volcanic CO2, got even thicker, hotter, and the oceans turned acidic. The evidence for this is in the rocks. Immediately above the glacial deposits, there are layers of carbonate rock, limestone, thick, extensive, globally distributed. Geologists call them cap carbonates, and they're bizarre because carbonate rocks normally form slowly over millions of years. But these cap carbonates formed fast, in a few thousand years, maybe less. They're the product of ocean chemistry going haywire. acidic water loaded with dissolved carbon dioxide, suddenly neutralizing and precipitating calcium carbonate in massive quantities. A chemical snowstorm, the signature of planetary-scale carbon cycling out of control. And in the aftermath, something changed, permanently. Oxygen levels spiked, not to modern levels yet, but close, maybe 18 to 20%. Phosphorus flooded into the oceans from freshly weathered continents. Nutrients were abundant. The climate was warm, stable. And for the first time in Earth's history, all the ingredients for complex, large multicellular life were in place. The environment was ready. The genetic toolkit, refined over 1 billion years of stagnation and punctuated by predation and sex, was ready. The starting gun finally fired, and life exploded. Within 50 million years of the Marinoan deglaciation, the first large, complex, multicellular organisms appeared. The Ediacaran biota, strange, soft-bodied creatures. Some of them resembled modern animals. Others looked like nothing that exists today. Fronds, quilted discs, segmented tubes, ranging in size from millimeters to over 1 meter long. They weren't quite animals. Not yet. Most of them lacked mouths, guts, obvious organs. They seemed to have absorbed nutrients directly from the water, like living sponges or bacterial mats scaled up to macroscopic size. But they were complex, multicellular, differentiated, and they were everywhere, in shallow seas across every continent. For the first time in 4 billion years of life on Earth, you could see biology with the naked eye. You could walk along a Ediacaran shoreline and see life, not just as green scum or microbial mats, but as distinct organisms, individuals, bodies. The Ediacaran lasted from 575 to 541 million years ago, and at the end of it, most of those strange creatures disappeared, went extinct, replaced by something new, something more familiar. Animals, real animals, with mouths, with guts, with skeletons, with predators and prey and ecological complexity beyond anything the planet had ever seen. The Cambrian explosion, 541 million years ago. Every major animal phylum appearing within 10 to 20 million years. Arthropods, mollusks, chordates, echinoderms, the works. But here's the thing. The Cambrian explosion didn't come out of nowhere. It was set up by the Boring Billion, by Rodinia, by the Sturtian and Marinoan glaciations, by 1 billion years of evolutionary experimentation in a low-oxygen, low-nutrient, stagnant world. All of that stagnation, all of that waiting, all of that frustration, it wasn't wasted. It was necessary. Because evolution doesn't happen in a vacuum. It happens in response to pressure, to challenges, to environmental stress. The Boring Billion was boring because nothing was pushing life to evolve. Rodinia was stable. The climate was stable. Oxygen was low but stable. Nutrients were scarce but stable. There was no crisis, no catastrophe, no urgency. And without urgency, evolution idles. Life does what works. It repeats. It stagnates. But the moment Rodinia started breaking apart, the moment the climate destabilized, the moment the planet plunged into back-to-back snowball events, everything changed. Suddenly, there was pressure, urgency, a need to adapt or die. And life, which had been quietly developing the genetic and cellular machinery for complexity over hundreds of millions of years, finally had a reason to use it. The paradox of the Boring Billion is that it wasn't wasted time. It was preparation time. Evolution was loading the gun, building the tools, refining the mechanisms, waiting for the right moment. And when that moment came, when the environment finally shifted, when the planetary stalemate broke, Life was ready. And it didn't just recover, it exploded. But here's the uncomfortable question, the one we need to ask ourselves. Are we creating another boring billion? Not through stagnation, through the opposite, through too much change, too fast. The boring billion ended because Earth's climate became unstable, because Rodinia broke apart and triggered glaciations and rapid environmental shifts. And those shifts, as catastrophic as they were, drove evolution, forced life to adapt, to innovate, to become complex. Today, we're destabilizing the climate again, but not through tectonic breakup, through carbon emissions, through deforestation, through industrial activity. We're pushing the planet toward a new state, a warmer state, and we're doing it faster than any natural process in the last 50 million years. The question is, what happens after? If we push Earth into a new, hot, stable state, a hothouse equilibrium, what happens to evolution? Does it accelerate, or does it stall? Because stability, remember, is the enemy of evolution. If the climate stabilizes in a new configuration, if it stays there for millions of years, if there's no pressure, no disturbance, no chaos, evolution slows. Life adapts to the new conditions and then idles, waiting, just like it did during the boring billion. And here's the terrifying part. During the boring billion, simple life, bacteria, and single-celled eukaryotes survived just fine. They didn't evolve much, but they didn't go extinct either. But complex life, multicellular life, that didn't exist yet. It couldn't emerge because the conditions weren't right. The environment was too stable, too limiting, too boring. What if we're creating a world where complex life can't persist? Not because we make it too hot or too toxic, though we might, but because we make it too stable, a new equilibrium, a new stalemate, where the survivors are bacteria and algae and extremophiles, organisms that can handle the heat and the acidification and the anoxia. And everything else, everything complex, everything large, goes extinct, not in a dramatic catastrophe, but in a slow, grinding decline, an evolutionary arrest. That's the real warning of the boring billion. It's not that Earth became uninhabitable, it's that Earth became unchanging. And in an unchanging world, complexity dies, slowly, quietly, boringly. In 2017, those geologists in Oman stood in the desert, staring at a stromatolite that hadn't changed in 800 million years. And they realized something profound. Stagnation isn't peace, it's death. Evolution requires chaos, requires disturbance, requires the planet to be dynamic, unstable, dangerous. Because only in danger is there opportunity. Only in crisis is there innovation. The boring billion ended because Earth became dangerous again, because the climate destabilized and glaciers advanced and life was forced to adapt or perish. And the organisms that adapted, that survived, became us, became every animal that's ever existed. The entire history of complex life, from jellyfish to dinosaurs to humans, exists because the boring billion ended, because the stalemate broke. The question we need to ask ourselves is, are we ending our own age of complexity? Are we creating a new boring billion, a new stagnant equilibrium where only the simple survives? Where intelligence, consciousness, everything that makes us human becomes a brief, doomed experiment, a flash in the pan, a footnote in a fossil record that will, a billion years from now, show a sudden decline, a boundary layer, a catastrophe not of fire and ice, but of boredom, of unchanging, relentless evolutionary stagnation. That stromatolite in Oman is still there, still unchanged, still waiting. A monument to a billion years of going nowhere. A reminder that survival isn't the same as thriving, that existing isn't the same as evolving, that time without change is just time. Empty, wasted, boring. 1 billion years ago, Earth was stuck, and it took a planetary catastrophe to get unstuck. 2 of them, actually, back to back. The Sturtian and Marinoan snowballs, 50 to 100 million years of global ice, followed by superhot deglaciations, ocean acidification, ecological collapse, and then, finally, recovery, innovation, complexity, life becoming what we recognize today. We don't have 50 million years. We don't have catastrophic glaciations to force evolutionary adaptation. We have decades, maybe a century. And the changes we're making aren't creating instability. They're creating a new stability. A hot, acidic, low-oxygen stability. A world that looks, chemically, a lot like the boring billion. Low diversity, low complexity, high microbial abundance, simple life thriving, complex life struggling. The real horror of the boring billion isn't that it was deadly, it's that it wasn't. Life survived just fine. It just didn't do anything interesting for 800 million years. And if we're not careful, if we push Earth into another stagnant equilibrium, we might create another 800 million years of nothing. A second boring billion. Except this time, we won't be around to see it end. Because unlike bacteria, we can't wait. We don't have evolutionary patience. We have lifetimes, generations, centuries at most. And in a boring world, a stagnant world, a world without change, complex life doesn't persist. It fades, and eventually it disappears, leaving behind only the simple, the bacterial, the microbial, life that can wait, life that doesn't need intelligence or creativity or curiosity, life that just exists, unchanging, uncaring, boring. 1 billion years ago, Earth was a prison, locked in stagnation, waiting for the walls to crack. And when they finally did, when Rodinia broke apart and the ice advanced and the planet was thrown into chaos, life didn't just survive. It thrived. It exploded. It became everything. The question is, will we? Or will we build our own prison? A climate so stable, so unchanging, that evolution stops, that complexity becomes impossible, that the future belongs not to intelligence, but to slime. The rocks in Oman don't answer that question. They just stand there, silent, layered, unchanged. A memory of a time when Earth forgot to evolve. A warning that survival and progress are not the same thing. That time, without transformation, is not a gift. It's a trap. 1 billion years ago, Earth was boring. And it took 2 apocalypses to make it interesting again. Let's hope we don't need a third. But let's back up. Because there's a piece of this story we need to examine more closely. A piece that explains not just why the boring billion was boring, but why it ended the way it did. And it has to do with something we haven't talked about yet. Something invisible. Something that, until very recently, scientists didn't even know to look for. We need to talk about the deep biosphere. Again. Because 1 billion years ago, while the surface world was locked in evolutionary stasis, something was happening below, deep below, in the crust, in the rocks. In places where sunlight had never reached and never would. Remember the Kola super deep borehole from our previous video? That Soviet drill that punched 12 kilometers into the earth and found organic carbon and liquid water at depths that should have been sterile. That wasn't a fluke. That was evidence of a global subsurface biosphere. a hidden world of microbial life living in the pores and fractures of rock, kilometers beneath our feet, surviving on chemical energy alone. No sunlight, no photosynthesis, just chemistry. Water reacting with rock, producing hydrogen, methane, simple compounds that bacteria can metabolize. And 1 billion years ago, that deep biosphere was thriving, probably more than it is today, because the Earth's interior was hotter then. More geothermal energy, more chemical gradients, more opportunity for chemosynthetic life. And while the surface biosphere was starving, limited by low nutrients and low oxygen, the subsurface biosphere was doing just fine. Hidden, patient, waiting. In 2016, a team of researchers led by Magdalena Osborne at Northwestern University published a study analyzing carbon isotopes in carbonate rocks from the Neoproterozoic. They found something strange, a persistent signal throughout the boring billion of methane production. Lots of it. Not from surface photosynthesis, from methanogenesis. Methane-producing archaea living deep in the crust, metabolizing hydrogen and carbon dioxide, pumping methane into the groundwater and, eventually, into the oceans and atmosphere. This deep methane production had consequences, big ones, because methane is a greenhouse gas, a powerful one. And during the boring billion, when atmospheric oxygen was low and there weren't many aerobic bacteria around to consume methane, that methane accumulated, not to Archean levels, but enough to matter, enough to keep the planet warm despite the sun still being dimmer than today. The deep biosphere, invisible and ignored, was acting as Earth's thermostat, keeping the surface habitable, preventing a runaway icehouse, until it didn't. Around 800 million years ago, something changed in the deep. The geothermal heat flux began to decline. Not dramatically, not suddenly, but noticeably. The mantle, cooling over billions of years, was becoming less vigorous, less active. And with less heat, the deep biosphere's productivity declined. Methane production dropped, and atmospheric methane levels, which had been stable for hundreds of millions of years, started to fall. At the same time, oxygen levels were rising, thanks to the Tonian oxygenation event. And oxygen, remember, destroys methane. The two react, oxidize, forming carbon dioxide and water. So you had a double whammy, less methane being produced, more methane being destroyed. The greenhouse was collapsing, and the planet, which had been warm and stable for so long, started to cool. This is why the Sturtian glaciation happened. Not because Rodinia's breakup alone caused cooling, though that contributed, but because the deep biosphere's methane output, which had been propping up the climate for hundreds of millions of years, failed. The thermostat broke, and Earth, no longer insulated by that invisible microbial greenhouse, plunged into the deep freeze. It's a humbling realization that the stability of the boring billion, the very stagnation that prevented complex life from evolving, was maintained by microbes living in rock. Organisms we've only discovered in the last few decades. Organisms that most people don't even know exist. And when those organisms faltered, when their metabolic output declined, the entire planet paid the price. Snowball Earth. Twice. But here's the kicker. The deep biosphere didn't go extinct. It survived. Of course it did. It had survived every catastrophe in Earth's history. And during the Sturtian and Marinoan glaciations, while the surface froze and most surface life clung to hydrothermal vents or cryoconite holes, the deep biosphere just kept chugging along, metabolizing, reproducing, waiting for the surface world to thaw, And when it did thaw, when volcanic carbon dioxide finally broke the freeze and the ice melted and the oceans flooded with nutrients and oxygen spiked, the deep biosphere was ready. Because it had been refining its metabolic strategies for billions of years. It knew how to handle extreme conditions. It knew how to survive. And when the surface biosphere exploded into complexity, the deep biosphere provided the foundation, the microbial mat, the recycling system, the engine of biogeochemical cycles that made complex ecosystems possible. We think of evolution as something that happens on the surface, in the sunlight, where we can see it. But some of the most important evolutionary innovations in Earth's history happened in the dark, below, in the crust, in the deep, hot biosphere. And 1 billion years ago, that hidden world was as important to the planet's future as anything happening in the seas. But let's get back to the surface. Because there's another mystery we haven't solved. Another piece of the puzzle that explains why complex life took so long to appear. And it has to do with oxygen. Again. But not the amount of oxygen, the distribution. Today, oxygen is everywhere. In the atmosphere, dissolved in the oceans. From the surface to the seafloor, if you're in open water, you can find oxygen. It's mixed, circulated, distributed by currents and wind and the overturning circulation of the ocean. The planet breathes, and that breath reaches everywhere. But 1 billion years ago, oxygen was patchy. The atmosphere had oxygen, sure, 10 to 15%, maybe more during the Tonian spike. But the deep ocean was anoxic, oxygen-free, and not just the very deepest parts. The entire ocean below a few hundred meters, everywhere, globally. This is called ocean stratification, and it's a killer, literally. Because in an anoxic ocean, organic matter that sinks from the surface doesn't decompose aerobically. It decomposes anaerobically, through sulfate reduction, producing hydrogen sulfide, which is toxic, deadly toxic. And that hydrogen sulfide doesn't stay at depth. It diffuses upward, into the shallower waters, creating a toxic boundary layer. Imagine you're a eukaryotic organism living in the Neoproterozoic ocean. You need oxygen. Your mitochondria demand it. So you stay in the surface waters where photosynthesis produces oxygen. But you can't go too deep, because below a certain depth, the water turns toxic, hydrogen sulfide, anoxia, death. You're confined to a thin layer, a biological skin stretched across the ocean surface, a few tens of meters thick, maybe 100 in some places, but no more. And here's the problem. To become large, to become complex, to become multicellular, you need nutrients, you need food. And in a stratified ocean, all the nutrients, all the phosphorus and nitrogen and iron sink. They fall out of the surface layer, down into the anoxic depths, where they get trapped, locked away, unavailable. This is called a nutrient trap, and it's an evolutionary dead end. Because you can have all the oxygen you want in the surface waters. You can have all the genetic machinery for complexity. But if you can't access nutrients, you can't grow. You stay small, simple, starving. The evidence for Neoproterozoic ocean stratification comes from multiple sources. Iron speciation data, sulfur isotopes, biomarkers for anoxic conditions, and they all point to the same conclusion. The oceans during the boring billion were layered, oxygen on top, anoxia below, and life confined to that thin surface layer, going nowhere. But around 635 million years ago, after the Marinoan deglaciation, something changed. The ocean mixed, overturned. Deep water, rich in nutrients, surged to the surface, and surface water, rich in oxygen, penetrated the depths. The stratification broke, the nutrient trap opened, and for the first time in hundreds of millions of years, the entire water column became habitable. Why did the ocean mix? The leading theory involves the deglaciation itself. When the ice melted, it released enormous amounts of fresh water into the ocean. Cold, less water, which spread across the surface, disrupting the normal density stratification. At the same time, the superheated greenhouse atmosphere, loaded with carbon dioxide, drove intense storms, hurricanes, cyclones, powerful enough to churn the ocean, to break the stratification, to mix the layers. And once the mixing started, it didn't stop, because the continents, freshly exposed after the glaciation, were weathering rapidly, delivering nutrients, fertilizing the surface waters, which boosted productivity, which produced oxygen, which sank into the depths, oxygenating the deep ocean, breaking the anoxia, creating a positive feedback loop. More mixing, more oxygen, more nutrients, more life. This is the moment. This is when the door finally opened. Not just unlocked like it had been before, but flung wide, and complex life, which had been waiting in the wings for hundreds of millions of years, finally walked through. The Ediacaran biota appeared within 10 million years of the Marinoan deglaciation, and they weren't just barely scraping by. They were large, some of them over a meter long. They were diverse, dozens of species, different body plans, different ecological strategies, and they were global, found on every continent, in every shallow marine environment. This was the real explosion, not the Cambrian, the Ediacaran, because the Cambrian animals, impressive as they were built on a foundation laid by the Ediacaran. The Ediacaran organisms proved that large, complex, multicellular life was possible. They pioneered the strategies, the ecological niches, the body plans. And when they went extinct at the end of the Ediacaran, they didn't take their innovations with them. Those innovations were inherited, refined, weaponized by the Cambrian animals that came after. But here's a question nobody likes to ask. What if the Marinoan glaciation hadn't happened? What if Earth had stayed warm and stable after Rodinia's breakup? What if the climate hadn't destabilized? Would complex life have appeared anyway? Or would we still be stuck in the boring billion? A planet of single-celled eukaryotes, photosynthesizing, reproducing, waiting. The uncomfortable answer, based on everything we know, is probably not. Because evolution doesn't happen without pressure, without stress, without environmental forcing. The genetic capacity for complexity was there. The cellular machinery was there. The oxygen was there, all close enough. But the environment wasn't demanding it. There was no urgency, no crisis, no reason to become complex. The Marinoan glaciation provided that reason. It nearly wiped out the biosphere, and the survivors, the organisms that made it through, were the ones that could handle extreme conditions, that could adapt, that could cooperate, that could become complex. And when the ice melted and the oceans mixed and the nutrients flooded back, those survivors didn't just recover. They radiated, they diversified, they conquered. This is the pattern we've seen over and over in Earth's history. Catastrophe followed by innovation. The Great Oxidation Event wiped out 99% of life. But the survivors invented aerobic respiration. The Huronian glaciation nearly sterilized the planet. But the thaw led to the first eukaryotes. The Sturtian and Marinoan glaciations came closer than anything before to ending complex life before it started. But they created the conditions for the Ediacaran and Cambrian explosions. Disaster is evolution's fuel. Stability is its poison. And the boring billion, that long, stable, stagnant period, is proof. Life doesn't need peace, it needs chaos. Now let's talk about something we've been dancing around, something uncomfortable, the role of extinction, because we tend to think of extinction as bad, as loss, as failure. And on an individual level, for the species going extinct, it is. But on a planetary level, on an evolutionary level, extinction is necessary, essential, because extinction clears the board. It removes the incumbents, the established players, the organisms that have optimized for the current conditions and are now blocking everyone else. During the boring billion, the dominant organisms were cyanobacteria and simple algae. They had optimized for low nutrient, low oxygen conditions. They were efficient, successful, everywhere, and they weren't going anywhere. As long as conditions stayed the same, they had no reason to evolve, no reason to become complex. They were already winning. But the Sturtian and Marinoan glaciations didn't just stress the biosphere, they cleared it. They killed off huge portions of the cyanobacterial and algal populations, particularly the specialists, the organisms that were so well adapted to boring billion conditions that they couldn't handle anything else. And when the ice melted, when conditions changed, those niches were empty, open, available. And the generalists, the organisms that weren't perfectly optimized for the old conditions, but were flexible enough to handle the new ones, moved in. And in those empty niches, they diversified, experimented, evolved, became complex. This is called ecological release, and it's one of the most powerful drivers of evolutionary innovation. You see it after every mass extinction. After the Permian-Triassic extinction, the worst in Earth's history, the survivors radiated into dinosaurs and mammals. After the Cretaceous extinction, the survivors radiated into modern birds and mammals. After the Marinoan glaciation, the survivors radiated into the Ediacaran biota and, eventually, animals. Extinction isn't the end. It's a reset, a clearing, a chance for something new. And without it, without that periodic clearing of the board, evolution stalls. You get a boring billion, a world of incumbents, optimized, entrenched, unchanging. So when we worry about the current extinction crisis, the Anthropocene extinction, we need to be clear about what we're worried about. We're not worried that life will end. It won't. Life has survived worse, much worse. We're worried that we will end, that we're clearing the board, and that we won't be among the survivors, that the niches we occupy, the ecological roles we fill, will be taken by something else, something that doesn't need us, something that might not even notice we were here. And based on Earth's history, that's exactly what will happen. If we push the planet into a new state, a hothouse state, a high CO2, low oxygen, acidic ocean state. The organisms adapted to current conditions, including us, will struggle. Many will go extinct. But the generalists, the extremophiles, the organisms that can handle heat and acid and anoxia will thrive. And they'll diversify. And in a few million years, maybe 10 or 20, the planet will be full of life again. Just not our life. Not complex life. Not intelligent life. Microbial life. Simple life. Boring life. A new boring billion. Except this time, We caused it, and we won't be around to see it end. But let's not end on despair, because there's another lesson in the boring billion, a more hopeful one. And it's this: change is inevitable. Stagnation doesn't last forever. The boring billion ended. Rodinia broke apart. The climate destabilized. The oceans mixed. And life, which had been waiting for hundreds of millions of years, finally got its chance. The question is whether we want to be part of that change, whether we want to guide it, or whether we want to be swept away by it. Because here's the thing about catastrophes. They're only catastrophes from the perspective of the organisms that don't survive them. From the perspective of the survivors, they're opportunities. The Marinoan glaciation was a catastrophe for the cyanobacteria and algae that had dominated the boring billion. But it was an opportunity for the eukaryotes that became the Ediacaran biota. The Cretaceous extinction was a catastrophe for the dinosaurs, but it was an opportunity for the mammals. Every catastrophe is someone's opportunity. The question is, whose? Right now, we're in the driver's seat. We're the ones changing the planet, destabilizing the climate, altering the chemistry, clearing the board, and we have a choice. We can change course, slow down, try to maintain the current conditions, keep the planet in the state that allowed us to evolve, to thrive, to build civilizations. Or we can keep going, keep burning fossil fuels, keep emitting carbon, keep pushing the planet toward a new state, and hope that we're among the survivors, that we're generalists, not specialists, that we can adapt fast enough to keep up. But here's the problem. Humans aren't generalists. Not really. We're specialists. We've specialized for the Holocene, for stable climate, for predictable rainfall, for coastlines that don't move, for ecosystems that produce food we can eat. We've built our entire civilization, our entire way of life, on the assumption that the planet will stay the way it is. And it won't. It's already changing. And if we don't adapt, if we don't change our behavior, we'll go the way of the boring billion cyanobacteria, optimized for conditions that no longer exist, outcompeted by organisms better suited to the new world. That's the real warning of the boring billion. Not that Earth became uninhabitable, but that it became unchanging. And the organisms that thrived in that unchanging world were the ones that didn't need complexity, that didn't need intelligence, that could just metabolize and reproduce and wait forever. We don't want to be those organisms, and we don't want to create a world where those are the only organisms that survive. The stromatolite in Oman is still there, still layered, still unchanged, a monument to 800 million years of evolutionary stagnation, a reminder that time without transformation is not progress. It's just time, passing, empty, wasted. 1 billion years ago, Earth was stuck, locked in a stalemate, waiting for something to break. And when it finally did, when the catastrophes came, life didn't just survive, it transformed. It became something new, something complex, something capable of looking back at those ancient rocks and asking, why? How? What happened? We are the answer to that question. We are what happens when a planet breaks its stalemate, when catastrophe creates opportunity, when extinction clears the board and evolution fills the empty niches with something unprecedented. But we're also the question, because we're creating our own stalemate, our own catastrophe. And we don't yet know if we'll be the survivors or the casualties, the opportunity or the extinction, the next chapter or the final footnote. The boring billion ended because Earth became dangerous, unstable, unpredictable. And in that chaos, life found a way. Not the life that existed before, but something new, something better, something capable of surviving conditions that would have killed its ancestors. The question is whether we have that same capability, whether we can survive the world we're creating, whether we can adapt fast enough, change quickly enough, or whether we'll become another layer in the rock, another fossil, another curiosity for some future intelligence to find and wonder about. What were they? Why did they disappear? What did they do wrong? And the answer, preserved in isotopes and extinctions and atmospheric composition, will be simple. They changed their world faster than they could adapt to it. They destabilized their own climate, and they weren't flexible enough to survive the consequences. The boring billion lasted 800 million years. The Anthropocene has lasted a few hundred. A blink, a flash. But in that flash, we've altered the planet as much as the Great Oxidation Event, as much as the Marinoan deglaciation, as much as any catastrophe in Earth's history. The difference is those catastrophes were driven by geology, by biology, by forces beyond any organism's control. Ours is driven by choice, by decisions, by actions we could change if we wanted to. That's both terrifying and empowering, because it means we're not victims, we're participants. We're creating this catastrophe, which means we could also stop it, or at least slow it. Give ourselves time to adapt, to adjust, to find a way to survive in the world we've made. But time is running out. The climate is already changing. The extinctions are already accelerating. The ocean is already acidifying. The ice is already melting. We're already in the catastrophe. The question is how deep into it we go, how far we push before we pull back. Because here's the final lesson of the boring billion. The catastrophes that ended it, the Sturtian and Marinoan glaciations, didn't just stress life. They nearly ended it. They came within a hair's breadth of sterilizing the planet. And only luck, geological patience, and a few scattered refugees kept life going long enough for the ice to melt. We might not be that lucky. We might push too far, cross too many thresholds, trigger too many feedbacks, and find ourselves in a world where the refuges aren't enough, where the catastrophe is too severe, where complex life, including us, doesn't make it. Or we might pull back, change course, stabilize, and survive. But survival isn't guaranteed. It never is. The only guarantee in Earth's history is change. And the only organisms that persist are the ones that change with it. 1 billion years ago, Earth was boring. And it took 2 apocalypses to make it interesting again. Let's hope we're smart enough not to need a third.